Hello and welcome to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and today we're going to be doing Unit 8, Lesson Number 2, More Work with Vectors. I know it's a flashy title for the lesson, but really it gets at the heart of things. With vectors, there's a lot of different things that we have to get used to. Their notation, the way they operate, their similarities, and importantly, their differences to scalars or just normal numbers. So all of that we're going to be working through really in the next few lessons. So let's jump right into it. Excuse me. Now, in the last lesson, we talked about breaking a vector down, especially a two-dimensional vector, into its independent component parts, right? There are many different ways, depending on what field that you're working in showing how these vectors get broken apart. The most standard way is writing it in this basis vector component. So in other words, if we have a vector that kind of looks like v equals 3i plus 2j minus 5k, excuse me. What that means is that it points 3 units in the positive x direction, 2 units in the positive y direction, and 5 units in the negative z direction, right? But we can, as long as we know what those components are, we can designate it in a few different ways. So for instance, sometimes these kind of strange looking brackets or parentheses are used. If we took the above vector and wrote it in this notation, it would just be 3, 2, negative 5. Now, quite possibly the most confusing notation, but it is one that the AP, the Advanced Placement exam, uses sometimes in calculus, is writing it as if it's almost a coordinate point, right, with normal parentheses. Again, we'll always know whether it's a coordinate point or whether it's a vector simply by the context that we're working in. So obviously pay attention to what's going on. Okay, but each of these just goes to taking a vector and showing how it's been broken down into its independent components. Okay, I'm going to clear out this text. Okay, it's gone. Let's take a look at exercise number 1. Now, obviously, part of vectors is being able to read them, and part of that is just being able to recognize what it's talking about. So take a look at exercise number 1. It says, given that u is equal to 5i minus 12j, find this. All right, so what is that? Pause the video for a minute if you need to, but just think about what they're even asking for. All right, they're asking for the length or magnitude of vector u. All right, well, let's visualize vector u. We can think of vector u as being something that goes 5 units to the right and 12 units down, and these are independent, they're perpendicular to each other. So really what we're doing is we're sort of breaking down the vector into the sum of 2 vectors, right? Remember, we sum 2 vectors by connecting them tail to tail. So this really is vector u, and the question is, how do we find its length? Pause the video now and try to find the length of u. Did you do it? It's just the Pythagorean theorem, right? Maybe we'll call that c, right? So we'll say that c squared is equal to 5 squared plus negative 12 squared, and eventually we'll get c is equal to 13. Now, more to the point though, right, we can always find the length of a two-dimensional vector by simply squaring its x component, squaring its y component. The negative is irrelevant because once we square it, it'll turn positive, and giving us our overall length. Now, letter B, we have a 3-dimensional vector. A little bit tricky, but this is essentially the same as asking what the distance is between the point 0, 0, 0 and the point negative 2, 7, negative 3. Now, what hopefully you've learned before in 3-dimensional coordinate geometry is that the Pythagorean theorem can be extended to actually 3 dimensions and upwards. So because these 3 components are independent of each other, and in fact are at 90-degree angles to one another, we can actually just say that the length of v is equal to the square root of negative 2 squared plus 7 squared plus negative 3 squared. And again, really you have to just be careful here. You have to make sure that when you're squaring these quantities, you don't do anything silly with negatives and positives, right? But we'll get what? 53/62, not the nicest answer, but whatever. So the length of v is the square root of 52. It's impressive. Any vector that's broken down into its component parts, you can always find its magnitude or its length by squaring each component, adding them together, and taking the square root. Take a look at exercise number 2. An object has a velocity vector given by 8i minus 4j, where the scalar components of the velocity have units of feet per second. Find the magnitude of v, and using correct units, explain the physical significance of this quantity. So I'd like you to do the whole problem. Pause the video now and see what you come up with. All right, well, we don't really have to draw it out, but you know that's not going to stop me. So if I really wanted to visualize this velocity vector, I'd say, well, it's comprised of the vector 8 going directly to the right and the vector 4 going directly down. So this is a visualization of the vector v. It's good to do so, right? Actually, finding the absolute value or the magnitude of v is very simple, right? We'll take 8 and we'll square it. The only reason I'm using parentheses in here is to really remind me with the negatives that I've got to square them. So 64 plus 16 gives me the square root of 80, right? And there we are. There we have it. That is the length of our vector. Now the question is, what are the units, and what does it really mean, right? Remember, you can track units, so let's keep track of this. That 8 was in feet per second, but then we squared it, so we got feet squared per second squared. Now we also added another feet squared per second squared, but ultimately we eventually take the square root, and we have root 80 feet per second. So the units are the same units of velocity. But what is it? What is root 80 feet per second? What physical significance is that? I hope you figured it out. It's the speed, right? Remember, in one-dimensional motion, the speed was the size of velocity. And that's exactly what it is in two-dimensional motion, and three-dimensional motion, and 15-dimensional motion, as if that's actually possible, right? Speed is still simply the size of the velocity vector, right? It's kind of cool. So I'm going to clear this out. Please copy down anything you need to. Okay, here we go. Let's go on. All right, let's move on. Now, with every vector, right, there's really two things. There's the size of the vector, and there's its direction. So yesterday, we took a vector of known size and known direction, and we broke it into its component parts. Today, we've already seen vectors in component parts, and we've used them to find the length of the vector. Now we're going to use them to find the angle of the vector, but we're only going to work in 2D. Once you start talking about the direction in 3D vectors or above, you have to bring in more than one angle, and we're only going to work at least in terms of the direction of vectors in 2 dimensions. So let's take a look at exercise number 3, where I use that third notation for vectors, one that looks like a coordinate point but is not. So I tell you that you've got the vector u, which is 7 in the positive x and 2 in the negative y, or negative 2 in the positive y, or whatever. We want to find the angle theta that this vector makes with respect to the positive x direction. Draw a diagram to illustrate this vector and your answer. All right, let's draw it. So this vector is composed of adding 2 vectors, one that has a length of 7, one that has a length of 2, and again, I'll draw my overall vector in red. Now, I want to know this angle. That's what I want to know. I always want to know the counterclockwise angle from due east. That's what I want to know. Now, what would be helpful is if I figured out, I'm going to go back to blue, if I figured out this angle, right? Now, I can always do that by using very simple trigonometry. In fact, I can say that the tangent of alpha is 2 divided by 7. Please notice that I dropped the negative here. I'm really working within a triangle where all the side lengths are positive. All right? I can easily use my calculator now to find the inverse tangent of 2/7, and that'll be ugly, 15.94 degrees. And theta will be simple enough. It will be 360 minus alpha. Simple enough, 344.055 degrees. All right? So that's not so bad. Every time you're given a two-dimensional vector in its component parts, you can draw a picture of the vector. You can use the inverse tangent to find a, if you will, reference angle. And then you can use that reference angle with some very, very, very easy geometry to figure out the direction angle with respect to due east. All right. I'm going to clear out this text before we go on to the last problem. All right. Let's do it. It says, find the angle that each vector makes with respect to the positive x direction, due east. In each case, draw a diagram illustrating the vector and the angle you find. So what I'd like you to do now is I'd like you to pause the video, find both of these angles. They're going to be kind of ugly, and draw diagrams, but take as much time as you need to. Okay, let's do it. Diagram first, answer second. All right, in this particular situation, we have an x component that's negative, so moving to the left, and a y component that's positive, so moving upwards. 3 units this way, 6 units this way, and again, let me draw my vector in red. My actual vector looks like this. All right, now I need to find this angle. That's the theta I care about, but the one that's going to be relatively easy to find will be this angle here, so I'll call it alpha. I'm going to say tangent of alpha is equal to 6/3. So alpha will be the inverse tangent of 6/3, or 2, whichever you want. That's going to be easy enough. That's going to be 63.43, etc. And now theta, the angle I need, will be 180 minus alpha, which will be 116.565. Yeah, that's what I got, accurate to 3 decimal places. All right, I'm going to give you one more chance to pause the video in case you were still a little bit unsure. Pause the video now and work on letter B if you haven't already. Okay, let's do it. In this case, right, we have a vector that has both a negative x-word component of 6 and a negative y component of 1. So the vector that I care about is this. All right. The angle I want is this. And the angle that I'm going to actually find to begin is this. Right? And again, it's the same song. Tangent of alpha is 1/6. Alpha is the inverse tangent of 1/6, which is small, 9.4623, etc. Don't know why I wrote it out that much. And theta now will be 180 plus alpha. This should seem very familiar to solving trig equations. So theta is 189.462 degrees. And that's it. That's the whole deal. So it's interesting. You know, one of the foci points, or focus points in the last lesson, was to take a vector whose length and direction we knew and change it into its component parts. You know, the A and the B with AI plus BJ plus CK, whatever. Here, though, in this lesson, we've primarily concentrated on going in reverse, which is, given a vector in component form, can we find its length, regardless of whether it's 2D or 3D, and can we find its direction angle only in the case where it's two-dimensional, right? So, backward, forward kind of motion. I'm going to clear out the text here, so copy down anything you need to. Okay. All right. Well, that wasn't too bad, right? Little chunk of vectors there. So this has been Unit 8, Lesson 2, More Work with Vectors, another Math 4 Honors Arlington High School math lesson. I'm Kirk Weiler, and until next time, keep thinking and keep solving problems.